wires.
Perfect.
Don't shake them.
Okay, in 10 or 15 minutes we're going to revise.
You have to twist out everything. No. Yeah.
We are going to go back over this chapter which we covered yesterday. Okay, so the notes are on the board. You've got a copy of them here, and as you see, it's only one page. The only thing extra to this are the maths questions. So I'll finish up by going over the maths one. Right? It's basic stuff, but we use this, as I said, for the next 6 or 8 weeks. We're going to be invoking the concepts of current, charge, and from that, the next chapter, which is potential difference. And the third concept is the third chapter. What's the third thing we said that goes with these two? Current, potential difference, and resistance. So to know what the current is, you have to know how hard it's being pushed, and you have to know what the resistance in the circuit is. So the three concepts go together. And we said rather than using the term voltage, we use the term what?
Volts.
Instead of voltage, if I were to say the voltage across 2 points is 3 volts, I shouldn't say the voltage. Nope.
Potential difference.
Potential difference. We haven't covered it yet, but it will actually be potential difference. The reason I'm saying that is because the everyday language we use will get mixed up with the science and physics terms we use here, and it'll seem a little bit complicated. So if I say something like, the electricity that we use up is something or other, that term electricity isn't actually a physics term. It isn't actually a science term. Electricity is like a catch-all phrase that talks about current, potential difference, and resistance. But there is no unit of electricity because it doesn't represent any one concept. So it's like an umbrella term for the different bits and pieces. We talk about current, we talk about the units of current. Resistance, the units of resistance. Potential difference, the units of potential difference. But electricity is just a general term. So even when you hear people saying things like electricity got used up in the battery, it's not correct to say that. So you've got to break it down and say, in fact, it's not even correct to say that anything gets used up in a battery, but you certainly wouldn't say electricity, right? So electricity is a general term. We try not to use it here, but it's a general term to describe maybe all the chapters that we're covering at the moment. Okay? So we start off by looking at current and charge, 3 effects of an electric current, and this overlaps quite a lot with what you've done in junior cert. Heating effect, how would you demonstrate the heating effect of an electric current? Sean? Bulb, what about a bulb? Make a circle with a bulb in it. And heating effect, so how do you demonstrate it's getting hot?
Make some idiot touch it.
Ah, very good. Except we don't like idiots, not that we've got anything against idiots. What's wrong?
No, I didn't. It's fine.
Yeah, it's fine.
It's fine.
Not that we've got anything against idiots, but in physics we want to, so the idiot is going to say, ah, that's hot. And I look at him and say, how do you know it's hot? He said, because it feels hot. And I want to say, but I don't believe him. How do you demonstrate to speak to non-believers that you've got a heating? Okay, you could look at a burn, but you can just as easily get a burn from freezing.
Thermometer up next to it.
Ian, talk to me. Put a thermometer up
Put
next.
the thermometer next to the bulb.
And you should see.
It's cool.
Right. So the notion here, and it's a big concept in physics, is that you take the human out of the experiment. So it's no longer reliable on subjective concepts, like a person thinks, oh, that seems to be getting hot. Because what's hot to one person mightn't be hot to another person. So you take the human out of it and you put objects in there, like a thermometer. Another example, sillier one, an even more basic one, just a kettle. You plug in the electric kettle. How do you quantify that it's getting hot? Okay, you could actually boil it. But again, just to demonstrate even quicker than that, stick your thermometer back into it. Okay? So you're taking the human element away from it, but it's a nice quick demonstration of it, right? Magnetic effect. How do you demonstrate the magnetic effect of an electric current?
Yeah, I'm fine.
Make an electromagnet.
Make an electromagnet, that would do.
You put the wire to the card and then get the plotting compass.
Put a wire to it, do with the wire.
You have to make a solenoid.
A coil.
Or not even a solenoid, but what you have to do with the wire in order to make it. What do you have to do in order to make an electric current?
Charge.
You've got to put charges going through it, so you've got to attach it to a potential difference. So here we go. One of these little guys here. There's your circuit, an electric circuit, so all you've got to do to demonstrate it, close the circuit, and what should happen? It's got a magnetic field associated with it, so as soon as you turn on the current by closing the switch here, it deflects the magnetic compass. The magnetic compass is only a piece of metal, and it reacts to the magnetic field with the current going around it there. So if you want to demonstrate the magnetic effect associated with a current, just get a simple current going in a circuit, and all you need for that is a wire and a battery. The only other thing you need is a little magnetic compass that will react to the magnetic field associated with the battery there. Okay, that's all there is to that. So I can close that one. We were then looking at the third effect, which is the chemical effect. How would you demonstrate a chemical current?
Can you do with sodium sulfate?
What would you do with sodium sulfate?
I don't know, I saw the board yesterday.
Easier, again, all of this is junior cert.
You put two like electrodes in some water or something.
Put 2 electrodes in water, and what do you get?
Splits the water
Into hydrogen and oxygen. I mean, here's H2O, so it splits it up into hydrogen and oxygen. You want to gather the 2 gases, so you put little test tubes above them, and then you want to test for carbonate, you want to test for oxygen, you want to test for hydrogen. So what you're doing is you're showing that the water is being split up into the 2 gases, and that therefore is a chemical effect of an electric current. Straightforward. Use page 245, and they put all of that together in one big circuit on page 245. But once you can remember each of the 3, it's a lot of this stuff is pretty basic. It doesn't get asked. Like, you won't be asked to define a conductor or an insulator. You might at ordinary level, but at senior level, we're just using this to get an understanding for the concepts. We're going to use it later on. So that's conductor, that's insulator. Electric current, we said, is a flow of charge. Back to my flow of charge. That there is a flow of charge. If you imagine that to be a little like a little light bulb, or it doesn't matter what's going on there, you can focus on that?
Yeah.
It's a bit tricky. Right. So what are the orange bits and pieces? Or the yellow bits and pieces here?
Oh,
What do they represent?
Like protons.
Oh, yeah.
Not protons,
Neutrons.
not neutrons.
A mixture of protons and neutrons.
If that was a proton, and that was a proton, do you get electrons going through protons like
No.
that? So if electrons are going through, passing through things, what do you think they're passing by?
are they just atoms then?
Yeah, they're just atoms themselves. So if you were to zoom in on this, you would see most of it, we spoke about this before, this is almost completely empty space, right? But every so often in there, you've got an atom of, in this case, aluminium. So atoms of aluminium, atoms of aluminium, atoms of aluminium. An atom is made up of the protons, neutrons, and electrons. So there's the protons and neutrons in there, and very faint around them. If I stop this, we might have a better chance of seeing this. So let's stop the current. You might just be able to make out the faint dots around there. And that's representing the electrons of that atom. So an aluminium atom, protons, neutrons, and the electrons squaring around it. Protons, neutrons, the electrons squaring around it, right? Now, this is a little bit misleading, but sometimes even look at a misleading analogy can be useful, because around here are all those electrons. Now, when you apply a potential difference, what will happen to those electrons?
They'll move.
They will move. And this is the difference between a conducting material and a plastic material, like an insulating material. If I put a positive and a negative here in an insulator, the electrons won't be able to move. They'll feel the positive, but they'll be so attracted to the nucleus and to the bonds, the electrical bonds around them, that they won't move as a result. And that's what makes it an insulator. In this case, it's easy for them to leave. What's misleading about this guy is it suggests that the current, it suggests that if I attach a battery, the battery supplies electrons to the wire. So it's like if I attach the battery to the 2 ends here, the battery would supply electrons. Why is that incorrect?
Because the electrons are there.
The electrons are already there. All it's doing is it's making the electrons move around at a more quicker rate, or making them move around where they wouldn't before, or certainly, even if you increase the potential difference, you're making them move around more quickly. So it's misleading because it introduces the electrons. Now, if I make the current go bigger, it's suggesting that it's introducing more electrons, where all that's actually happening is it's making more and more of the electrons that are already there past the point in a fixed amount of time. So this brings us on to our notion of current. Current is a flow of electrons, right? And if the current is 1 amp, you're saying that 1 coulomb of charge passes by a fixed point per second. Remember we said 1 coulomb is a really, really big amount of electrons. So if the current is 1 amp, then 1 coulomb, which is a big amount of electrons, pass a point in 1 second. If it's 2 amps, then it's as if 2 coulombs pass per second. Okay? Back to the whole notion of, I can get rid of that.
What happens to the atoms if they lose an electron?
It's not... We'll see later on in semiconductors, there's a sort of a fixed amount of electrons, and when it loses an electron, what's left becomes positively charged, right? But here what happens is it's like this big swarm of electrons are surrounding all the atoms. So all that's happening is they're all just moving along like that. So it's not like any one electron in a metal is associated with a particular atom. They're shared between all the, and they start moving along like that. We were looking at electric circuits, which is the next thing I want to do, but we want to look at, I would start with here. We said the whole notion of conductors and insulators is a bit of a simplification. Is a human generally considered to be a conductor or an insulator? Generally considered to be an insulator, but we could show it to be a conductor. So here's a lovely little demonstration of this. And this is, if you're looking to revise electricity, I'll use a general term yourself, or particularly concepts like current, potential difference, you need to look at this website. It's the best one that's pretty much out there. And there are a lot of stuff out there. When I say this is the very best bar none, it means it's the very best bar none. It's a super educational tool. Partly because when we will do demonstrations with wires, it gets very complicated. You have bucket loads of wires going everywhere. You don't know what's going where. Where this is representing all of that scenario, but you don't have the finicky wires to worry about. So this is representing a wire. It's a copper wire, and what's nice about it is you can see the electrons in the wire. So the brown bit in the background of the atoms, and there's the wire. I want to bring out a second wire because I want to make a little circuit. I want to attach one end of it there. I want to straighten it up by putting the other end down here. Now, if I want the basic circuit, what else do I need for current to flow, did we say? Potential difference. So out we do, we've got that battery. There's my battery, nice and simple.
Can I borrow the optical boxes?
You certainly can borrow the optical boxes. They're just inside the door there. In fact, you also need slits, so give me 2 seconds. Don't go anywhere.
Can I stop it?
No, let it go.
Don't go anywhere.
Stay tuned.
These things on the develop particularly, it's funny, it's only, I only saw the 6-inch one because of the time the money. We are going to do this. So,
oh yeah, I know what you mean. Did you get the transformer? And the power supply is there. So you can ask her if she needs it first of all.
next time on
Back in action? Right, I grab one more wire. Grab the wire. There we go. Grab the wire. Thank you. Now, if I connect it up, what's going to happen? The electrons should flow. So it's the battery is supplying a push. Remember we said it's like it's pushing them. I'll actually show you up here. This guy here, it's like it's pushing the electrons in one direction, and this end of it is pulling them back in that direction down there. Okay? So I use the phrase or the analogy as if the battery is pushing the electrons around, but it's actually pushing them on one end and pulling them back in on the other end. So that's what the potential difference does. Now, if I push electrons around the circuit and there's no resistance in the circuit, what will happen to the electrons?
They will go quickly.
They will go very, very quickly. So quickly, in fact, that what might happen?
The battery will explode.
The battery may well explode, or these guys here, if that's in a little electrical cable. I'm going to show you one of these guys. Question is often asked, does it matter when you're putting in circuits whether you use black or red cable? Does it matter?
No.
Because it's all just an electrical wire, it's just covered with different colored plastic, just to indicate what's going on. And what you might happen, if you put this circuit together like that, you should actually notice the plastic itself starting to melt. Because
we did it with the battery last year.
you did it with a car battery?
Battery.
Yeah. So if you attach 2 ends of this to a car battery, the plastic will certainly melt. And the positive end to the really need to put the minus like that. You get probably not enough current. If you can come along, and yeah, you can come along, even though it'll supply enough current to this here to melt the plastic. Why can't it's safe for me to touch resistance? So a lot of current is no resistance, but yet if I'm touching it, nothing goes through me because I have such a big resistance. So back up here, if I connect these two guys together, nice and quickly, we should get a large amount of current. In fact, let's, and straight away the battery goes boom. So can I separate it? And we're back in business again. So what should I put in here? There's my little resistor there. Stick in right there. Now you're looking at a wire. You can't see, in this case you can see the electrons moving. Generally you can't see if the electrons are moving or not. So what would you like to show to demonstrate the current is flowing?
light bulb.
A light bulb would be a good idea.
Or fan.
Let's get a light bulb. Out you come.
Holy moly.
It's pretty impressive, isn't it? And it's all cheap. And there we go. So now you can just about see it like. If I want more electrons to flow, what can I do?
Take away the resistance.
Take away the resistance. Change resistance, remove the resistance, that back in there, and it's moving a little bit more quickly. What else can I do, Alex?
Put in 2 batteries.
Put in 2 batteries. Let's remove this guy, stick in another battery.
Put in 3 batteries.
Over there. Stick this guy over here.
Wow.
And it goes. So what's lovely about this is you've got the 3 ideas. You've got potential difference, which is pushing the electrons around. you have got the resistance, which determines how quickly it goes. And then finally, you've got the current, which is the flow of electrons itself. Okay, so the three things go together. And you can play with,
Which is the positive end of the battery?
That's our next thing right now. If you look at any battery, let's take one right out of here. And you look at it. Which is the positive end? Just take a look at it there. Alex, take a look at it there. And at the very back, take a look at it there. You can see each battery's got a positive end on it.
Yes.
So in this guy here, the one as you said with the bump at the top of it is the positive. Current flows which way? There's a positive and there's a negative. Current flows from the positive to the negative, or negative to the positive. Let's go back to this guy. See the black end here? If I take that battery out, can you see by looking at it which is the positive end?
Yeah. No.
I'm guessing the black one.
Can you see this end of it here? There's a little notch right there. Right? So that's the positive end. So that's the positive end. So which way is the current going?
Negative.
Positive.
In the positive, at the negative. Minus.
Okay.
Whoa.
Happy days. Right, I've held this right here. That's the positive end. That's the negative end of the battery. Current goes, you say, from positive to negative or negative to positive?
Negative, positive.
Positive.
Negative,
Positive.
negative, positive.
Check the notes that I gave you yesterday. Current, conventional.
Conventional.
Conventional current
Negative.
goes from positive to negative. So conventional current is going to go around like that, direction there.
But it's not though.
But what's not?
It's going the other way.
What's going the other way?
The electron.
The electron is going the other way. Remember when these boys put this stuff together, they thought these were positive charges going from a positive to a negative end, so they said that's the direction in which everything is moving. So we keep that convention. It's known as conventional current. It's going from the positive end to the negative end. Whereas in reality, what's actually happening is it's the electrons which are going that direction down there. So the electrons are going from the negative end and being attracted to the positive end. So we just keep an eye on that again. As soon as I do that, we'll probably lose these guys here. So we're saying the electron should be moving in that direction. The current goes in this direction. So we want to see that are those guys correct. And I don't remember myself which is which. Let's take a quick look at it here.
Yeah.
Yeah.
So these represent what?
Electron.
The electrons are going in that direction. And I don't think I can write here at all.
We're burning all the books.
Yeah, I don't think I can write there. So the electrons are going this end, even though the current is going to that end there.
You know when the light bulb blows
Ross.
like in the little copper bit?
Yep.
How much battery does it got since it's in
Fancy
resistor?
bulb.
Yeah, you'll find that basically, if you have a 6-volt bulb, that would be very, very thin. If it's a 40 or a 6 watt, it'll be normally measured in watts. And we'll see later on, we haven't done it yet. Watts is a measure of the volts, the potential difference, which is measured in volts, multiplied by the current. So, as soon as you ask the question, it will be determined by how thick that guy there is. And the thicker it is, the more current it can take through it. But when it blows, it's that little filament in there that actually blows generally. Okay, and again, in a light bulb, you don't normally see it, but there's got to be two connections. So if you have a normal light bulb, there's got to be a connection going into it, and there's got to be a connection going out to it. And it's not normally obvious which is which. But normally the casing is at one side of it, and the bottom the other side of it. Okay? We get rid of all of that. You can do lots of other things here. Oh yeah, you can test for conductors and insulators. Let's clear that. Let's go down here. And let's clear that if I can. Back to this guy. There we go. Clear that. Clear the circuit and start over. Yes. I now want to see if something is a conductor or an insulator. So out goes the wire. Out goes the second wire. What else do I need to see if something is a conductor or an insulator?
A light bulb.
A light bulb would be good. There's the light
It's a
bulb.
huge-
What else do I need?
Battery.
Battery would be good.
Tension.
What else do I need?
A human.
Mine's the thing you're going to test with.
Whatever it is I'm going to test. So let's check it out here. What would you like to test?
Use a penny. Use
A
a
dog.
Use the-
Use a dog.
Start off with a penny.
Dog.
Nice and easy.
Dog.
Where's my penny gone?
Is there
It's in the light bulb.
Back you come. What should happen?
What is that?
It will blow up.
That is a penny.
It's got a magnetic charge though. Like a penny.
It's got electrons on it anyways.
Yeah.
So should it be a conductor or an insulator?
Conductor.
So a penny is definitely a conductor. Now the only reason it mightn't be is because it might have some sort of metallic paint on it. But anyway, I can remove that little guy and we'll check something else.
Use a dog.
Use a
dog?
Anybody wants to check the dog?
Oh.
Let's take the dog out of the way. So we can for the dog. Aye, come out. You have to move the dog.
Touch your glass.
Go again. Grab the dog. Or you come out of the way. Good lad.
Good boy. Good doggy.
Get the other end out of the dog. That, by the way, is his fourth leg, so it gives me somebody else.
Why are you putting the second
Are you
one?
sure it's not his fifth leg?
So we're ready to go? Conductor insulator?
Insulator.
Definitely an insulator, there's nothing whatsoever happening here. Unless, how would you make him a conductor?
By ground.
Make it a really big current.
By putting in a heck of it. How do you get a really big current flowing?
More batteries.
Using lots and lots of
Take
batteries.
the light away.
No,
Like more batteries.
change the voltage. I don't think we can put it on.
Oh, yes, we can.
The dog can like.
Get two.
Make two. Come on, Scotty. Come on.
Just make a circle of batteries.
Yeah, I'm guessing they don't want the. They don't want to confuse things. One more time. Change voltage up to 100. Oh, the other thing here is 100 volts done. Nothing happening. Definitely a conductor.
Take it to the where the light bulb goes. This goes.
How long is this going to take?
Wow.
And there's fire.
Fire is always good. Okay, let's take
Awesome.
back up to the note we're just about to finish up with. Electric current, we said, is a flow of charge, right? It's measured in amps. And we said the unit of electric current is the ampere. The definition we come across later on, we said you won't like it because it's measured in terms of magnetic forces. It's the current effect. To determine how big current is, you look at the magnetic effect that it exerts on another part of a circuit or on another wire. And that determines how big it is. Go through it nice and quickly here. Got you.